Okay, so the first type of, or the first topic that you'll have on your exam is going to be oxidation reduction. So you're going to have this type of question where I ask you which species is oxidized and which one's reduced in a chemical reaction. You'll just get a different chemical reaction, obviously. So if you guys remember, oxidation is when you lose electrons. Okay, remember, oxidation is loss. And then reduction is when a species gains electrons. Okay, so remember the acronym oil rig, right? Oxidation is loss, reduction is gain. You can also do Leo grr if you like that for whatever reason, right? A lion goes grr, right? Losing electrons, oxidation, gaining electrons, reduction. Doesn't matter which one you use, whatever acronym works best for you. Those are the two common ones that I've seen in like textbooks and stuff. All right, so first thing we want to do is we want to determine the oxidation numbers on the reactant side first. So we have AS, and it's a solid. So this is a metal, so the oxidation number for this is going to be 0. Okay, so solid metals have an oxidation number of 0 because that's their elemental form. And Cl, this is just something you need to remember. This is a diatomic gas. This is going to also have an oxidation number of 0. Okay, diatomic gases are the elemental form for things like hydrogen, for nitrogen, oxygen, fluorine, chlorine. Basically, a lot of the nonmetals are going to have an a diatomic gas as their elemental form. Okay. All right, and then we're going to see how it changes on the product side. So let's take a look here. We know that chlorine's most common ion is -1, right? And there's 3 of them, so it's going to be -1, -1, -1. That means AS is going to be +3. Okay. All right, so we're going to see how the oxidation numbers change. So if we look at AS, it went from 0 to 3. That means it became more positive. So if it becomes more positive, that means it's losing electrons. So this is the one that is oxidized. Okay, so the oxidation species is AS. And then Cl goes from 0 to -1. So it becomes more negative. That means it is gaining electrons. Okay, that means Cl is going to be the one that is reduced. All right, so that's how you can determine. Okay, a couple things to remember. Just remember, metals in their elemental form metals are solids in their elemental forms. That's why this has an oxidation number of 0. And then Cl2, diatomic gas, that's its elemental form. Yes. Oxidation, AS, reduction, Cl. Oxy red. I'm sorry. Another day, another criticism of my handwriting. Oxidation, AS, and reduction, Cl. Okay. All right. Any questions about this first type of question? Again, you'll have something very similar to this on your test. I think on your homework as well, you have a couple problems like this. So if you want a little more practice, you can look at your homework to do these. All right, let's go to number 2, oxidation number of sulfur in Na2SO4. This is another type of problem you'll have on your exam. I'm going to give you a compound. You got to figure out the oxidation number of the one I'm asking for. So we're looking for sulfur. Now, the easiest way to do it is to identify this is an ionic compound with sulfate inside of it, SO4 2-. This is why I keep saying memorize your polyatomic ions, because this makes it really easy to identify sulfate in there. You don't have to do extra work. Okay, now, the other oxidation rule I said that's important is that oxygen is -2, right? And there are 4 of them. Okay, total of -8. And the overall charge of sulfate is -2. That means that sulfur and the 4 oxygens are going to equal -2 when you sum it up. So that means sulfur has to have an oxidation number of +6. Okay, so the oxidation of sulfur in this compound is +6. Okay, guys, let's go over number 3. So number 3 is asking you basically which of these are electrolytes and which are non. So it's very simple. Electrolytes are going to be compounds that dissolve in water. Okay, so they dissolve in water. And non-electrolytes obviously are the opposite. They don't dissolve in water. Okay, so I'm just going to write don't. Okay. Now, in terms of the actual chemistry, it's very easy to identify it. Electrolytes are going to be either ionic compounds or ions. Okay, ionic compounds or ions. Okay, Okay, because they're going to dissolve inside of water. We'll talk a little bit more in detail about the mechanics of that, I think, in Unit 8. But for now, just know ionic compounds or ions are electrolytes, and the non-electrolytes are going to be basically covalent compounds. Okay, so basically for this list, you just need to look through it and identify what are ionic compounds or ions and what are covalent. So let's go to A, NaOH. This is going to be an ionic compound, right? So this is going to be an electrolyte. NaOH is also a strong base, which is one of the things you need to memorize for your exam. One of the many things. All right, CH4. Okay, this is covalent. This is not an ionic compound. There's no ions inside of it, so this is going to be a non-electrolyte. Okay, this big old thing right here is made of 2 polyatomics, NH4 plus ammonium and SO4 2 minus sulfate. So since it's made of 2 polyatomic ions, it's an ionic compound. So this is an electrolyte. We got phosphate right here. This is an ion. We can see right away because it has a negative charge on it. And so this is an electrolyte. And then C2H4 is a covalent compound. So this is a non-electrolyte. Okay. So very easy way to distinguish them. Again, you'll have a question like this on your test as well. I keep saying that, but pretty much all these questions are going to be on your test, but just want to remind you guys. You will be given a list, and you got to identify electrolyte, non-electrolyte, so on and so forth. Okay, just look for ionic versus covalent. All right, number 4, it says that you have a solution that contains Ag+, Cu2+, and Pd3+, and then it asks you what is a solution you can add to cause no observable reaction. Okay, so I'm just going to draw it. You guys don't need to draw it if you don't want to. I know that nobody can keep up with my artistic ability, but these are the 3 ions, and they're floating around inside my container. Okay, and basically what the question is asking is, what is a chemical that you can put in here so that there is no reaction? Easy way to think about that is because there's ions. Easy way to think about no reaction is basically something that forms no precipitate. Precipitate.
So that would be NO3?
Yeah, exactly. So that's a great answer. So NO3, if you guys remember, is a compound that always dissolves in water, right? It's one of the ones you need to memorize. So you can basically write for your answer anything that contains nitrate, any ionic compound that contains nitrate. Okay, so if you want to be super specific, you can say like NaNO3. You can say something like KNO3. You can get specific like that. Or you can just basically say any compound that has nitrate inside of it. Yes. This? No precipitate. No solid. I'm sorry, guys. I feel so bad for you guys. So yeah, any compound containing a nitrate would be your answer. Okay, because it doesn't matter what the cation is, right? Because if you put any cation, positive and positive isn't going to react with each other, right? Like charges repel. So basically, you just need to pick something that might attract to these, but don't form a precipitate. The only one you have to memorize is going to be something that contains a nitrate. Okay, so if you want to get as general as possible, you can just say that you can write NO3 containing compounds. Okay, but I would also take an answer like very specific, like KNO3, NaNO3, RbNO3, if you want to get that specific. That would be a legitimate answer as well, but generally it's going to be anything that has nitrate inside of it. Again, make sure you make a note of this because you'll have a question like this on your test. All right, guys, let's start going over number 6. So number 6, first thing you want to do is you want to write your balanced equation. So I'll get rid of the balance part first, but let's talk about how we got it. So pretty simple on the reactant side. You got your base NaOH, and you got your acid right here, H3PO3, and they're going to react together. Now, remember, it's double replacement, so the Na is going to go to the PO3, but if you guys remember, Na is +1. PO3 is 3 minus, so you need Na3PO3. This is going to be your salt, and then since it's an acid and base, it's also going to form water, HOH. And then from there, just a simple balancing, you need a 3 here, and a 3 here. Okay. Okay, and if you look at this, it's the formatting of an acid-base neutralization reaction. You got a base, you have an acid, it's going to produce your salt and your water. Okay, so yes. No, you don't have, unless it asks you for it. Yeah. Yeah, if it's asking for like a complete ionic equation or net ionic equation, then yes. But because the equation is only helping you solve the problem, it's not the actual answer, you're good. Yeah, great question though. Yeah, so you don't need to include the states of matter unless it explicitly asks for it in the problem. Okay, so once we got our balanced equation, we can start we can start doing the stoichiometry. So it tells you that you want to figure out the milliliters of 1 molarity base to neutralize 1500 milliliters of a 0.7 molarity acid. So you're going to start with your acid first. So you have 0.75 molarity of your acid, and then you want to find moles, and then it's 1500 milliliters, so 1.5 liters. Okay, so we're going to multiply 0.75 by 1.5 in order to get our moles. Okay, so you multiply the two numbers together, and that's going to give you 1.125 moles of H3PO3. Okay, all we did was pretty much cross multiply. All right, now we're going to use the balanced equation in order to do the stoichiometry. So times, and then we want to get rid of our H3PO3, so we're going to put 1 mole of H3PO3 for every 3 moles. I'll try to color code this for you. 3 moles of NaOH. All right, now for this next part, you can just solve it and then put it into the molarity equation to solve it. But I'm just going to do it the dimensional analysis way, just to make it a bit easier. Actually, no, it might be a little more confusing for you guys. So I'll just solve it out. Sorry, ignore me. Okay, that'll give you 3.375 moles of NaOH. Okay, and then we know from the molarity equation that it's 1 molarity NaOH, 3.375 moles, and then we want to find, this is going to be liters. Okay, so if you want to rearrange the equation, it'll just be 3.375 times 1. Yes, of course. Okay, and that's going to be liters. So to do milliliters, just divide it by 1,000, 3375 milliliters. Okay, and that's pretty much it. That's the type of question you'll have. Just make sure you put in the unit of measurement it asks you for milliliters, so you got to divide by 1,000. Sorry, multiply it by 1,000. All right, so for number 7, first thing we want to do is we want to start with the 67 grams of lead. That's what we are trying to react with. So that's going to be our starting value. So 67 grams of Pb. Okay, so we want to convert this into moles using the molar mass of lead. So if you look on the periodic table, it's going to be 207.2 grams of Pb per every 1 mole. Okay. All right, that's going to convert it into moles, but we're not looking for the Pb. We're trying to figure out how much sulfuric acid can neutralize it, or sorry, react with it. So we're going to convert, and then this is going to be a 1-to-1 ratio. So 1 mole of Pb. If you guys look at it, it's already balanced for every 1 mole of H2SO4. And so you can just plug this into your calculator. Very simple calculation. It'll be 67 divided by 207.2. And so that means that you are going to need 0.32 moles of H2SO4. Okay. Now, we're not looking for the moles. We want to find the liters because we have the molarity of the solution we are working with. So it's going to be 0.25 molarity is equal to 0.32 moles divided by liters. And so if you guys do the math for this, it's going to be, the liters are going to equal 0.32 moles divided by 0.25 molarity. So you get about 1.29 liters. All right, guys. So I'm gonna go over the balancing part. If you're working, just feel free to work and check your answer. But you got barium nitrate, BaNO3, and you are reacting with phosphoric acid, H3PO4. Okay, and it's gonna be double replacement. So we got to do Ba and PO4 and H and NO3. Okay, so let's start with HNO3 because that's the easiest. It's gonna form nitric acid, HNO3. H is +1, nitrate is -1, so they balance each other out. And this is going to be aqueous because it has nitrate in it. Yes. Oh my goodness, you are right. Oh, I'm a failure. Thank you. BaNO3 2. Yeah, because Ba is +2. Thank you. Sorry about that. Okay, so Ba is +2, so it's BaNO3 2. My fault. Okay, so that's gonna be for H and NO3. Now we gotta do Ba and PO4. Now, Ba, like we said, is +2. PO4 is -3. So we gotta balance out the charges for this as well. And so barium phosphate is gonna be Ba3, PO4 2. Okay, so that's the tricky part about the equation. It's just figuring out how many of each ion you need. And then it said this is the precipitate, so this is going to be your solid. Okay. All right, so that is your equation, and then obviously we need to balance it. So if you guys balance it, it should be 3, 2, and 6. 6 night, HNO3. Okay, so the question is asking, after the reaction, what is the concentration of barium ions in the combined solution? Okay, so in order to solve this, what we first have to do is figure out initially what the concentration of the ions were to begin with. Okay, so let's take a look at the problem. It tells us that we start with 2 molarity and 100 milliliters of our barium nitrate. Okay, and then for our H3PO4, we're going to have 0.75 molarity, and it's going to be 100 milliliters. Okay, so same volume, different concentration. Okay, so what we're going to do now is we're going to look at the concentration of each individual ion in that solution. Okay, so for this, we're going to look at the concentration of just the Ba2+, and remember this bracket means concentration. Okay, and we're going to look now at the concentration of the nitrate. Okay, and we're going to compare the two together. All right, so if you guys take a look at the barium ions, there's only one barium ion in the entire molecule, right? And so that means the molarity of the barium ion is the same as the molarity of the entire compound. Okay, but the problem is how many nitrates are inside barium nitrate? 2, yeah, because we got the parentheses 2, which means the concentration is going to be double that of the entire molecule. So barium nitrate concentration is 2 molarity, but nitrate is 4 molarity because there's 2 inside barium nitrate. Okay. All right, let me give you guys 30 seconds. See if you can write the concentration of each ion in the H3PO4. Okay, guys, so for hydrogen, you should see that there are 3 hydrogens inside H3PO4, so we have to multiply the molarity by 3. That should give you 2.25 molarity. And then phosphate, there's only 1, so you can just have the same molarity. Does this part make sense? Because this is the part that kind of trips you up with the concentration. Okay, you just look at how many individual ions there are, and that gives you the ion concentration compared to the ionic compounds concentration. All right, so what we have to do now is we need to convert this into moles. So I want you guys to take about a minute, see if you can convert all of these molarities into moles, because that's going to tell you how many moles of each ion are inside of this solution. Okay, so convert each of the molarities into moles for me, and then I'll show you guys how to finish up the problem. All right, guys, so I have the equation for molarity right here. So molarity is moles over liters. So if you want to find moles, you just do molarity times liters, right? Now, it gives it to you in milliliters, but divide by 1,000, so that's 0.1. So basically what you want to do is just multiply each of these numbers by 0.1. So 2 molarity becomes 0.2 moles. 4 molarity becomes 0.4 moles. Okay, just move the decimal 1 time to the left for all of them. 0.225. And then lastly, 0.075. Okay. All right. Everybody good with that so far? Okay. Now is the other tricky part, is we're going to figure out basically how this reacts together. So we can see from our balanced equation that the H and NO3 are going to react together, right? But we don't really care about this because we're not concerned about HNO3, right? The question is asking for barium ions in the combined solution. So what we care about is basically this reaction right here between the barium and between the phosphate. That is what we are looking at. Okay. Okay, so these two things are reacting together. 0.2 moles and 0.075 moles. Okay, we're going to be looking at how this reacts together. All right, so what we want to do now is we're trying to figure out how much barium is going to be left over at the very end of this problem. Okay, now we got 0.2 moles of barium and we have 0.075 moles of phosphate. And so if we take a look at this reaction right here, we have a ratio, right? We have a ratio of 3:2. So every time we are making a barium nitrate, we are using 3 barium ions and we are using 2 phosphate ions. You guys see that? That ratio? And so what we're trying to do now is we're trying to figure out how much barium is going to be left over when these two quantities react with one another. Okay, so I'll give you guys about a minute. It's just working with the ratio. So see if you guys can figure out and calculate how much barium is left over after these two quantities react to make barium nitrate, or barium phosphate, excuse me. So try it out, see what you get. Again, you're going to use the ratio in the ionic compound, and then we'll go over it together. Alrighty, guys. So let's talk about how we can figure out how much barium we have left over. So to do this, we actually need to look at this in terms of limiting reagents, okay? Because you have 2 different starting quantities, and you want to figure out how much barium nitrate you can make with each. So let's start with just the Ba2+. Okay, so we have 0.2 moles of Ba2+, and what we're going to do is we're going to set up a just quick fraction to figure out how much of this we can make. Now, if we take a look at barium phosphate, we see that there are 3 moles of Ba2+ for every 1 mole of barium phosphate. Okay. Does this part make sense so far, guys? We're trying to figure out how much barium phosphate the barium ions can make. Okay, so what we're going to do is we're going to grab our calculator, and we just do 0.2 divided by 3. Okay, this is going to give you 0.0, and I'll do 67. I know. All right. The next one, we're going to look at phosphate now. So 0.075 moles of phosphate. And we're going to set up a fraction to see how much barium phosphate we can make. There are 2 moles of phosphate in every 1 mole of barium phosphate. Okay. And so what we're going to do is 0.075 divided by 2, and that is going to give you 0.0375 moles of barium phosphate. So this is how we're finding the limiting reagent. We're trying to figure out which one is going to run out first, how much barium phosphate we're actually going to make. Okay? So between the two, we always want to pick the smaller number, which means that we're actually going to make 0.0375 moles of barium phosphate. Okay, which means phosphate right here is our limiting reagent. We're going to run out of this first, which makes sense because the question is asking how much barium is left over in the solution. So that means this is going to be our excess. That's why we have barium just floating around. It's because this is what we have left over. Okay, now comes the hard part, because now we need to figure out how much barium is still left and did not get made. So what we have to do now is we take the amount we could have made using barium and subtract what we actually made. So what we're going to do is we're going to take our 0.067 minus 0.0375. Okay, that means that the amount we did not make was 0.0295 moles of barium phosphate. So this is what we did not make, even though we had enough barium. And this is going to help us calculate how much barium is left over. Okay, so what we're going to do is another dimensional analysis. So 0.0, I know you guys probably hate this problem, right? Just letting you know, this is on your test. Okay, you got this. So this amount of barium phosphate, you set up another conversion, and in every 1 mole of Ba3PO42, there are 3 moles of barium. And this is finally going to give us the actual amount of barium that's left over inside of the solution. But we're not done. I know. Because what are we looking for? We're looking for concentration. How do we measure concentration? Molarity. What do we have right now? Moles. So we have to take this and plug it in to the molarity formula. Isn't this fun, guys?
I'm not feeling good about
so much math.
I'm not feeling good with this test.
Okay. Okay, but there's actually another trick on this. Because look, we're using the molarity formula. I know, I'm so excited right now because I see you guys so sad. We're using the molarity formula. So let me ask you, which of these 3 variables are we looking for? We're looking for molarity. Good. Okay, I didn't trick you there. What is your number for moles?
0.08.
Yeah, 0.0885 moles. So that means we need to plug in liters, right? How many liters do we have in our solution?
200.
Oh, I didn't get you guys. Yes, it is 200. A lot of people look at 100 and say, oh, it's 100. But this is combined, right? So it's going to be 200 milliliters, okay, or 0.2 liters. You solve that, and that is your final answer. Dang it, I thought I got you guys. You guys are too quick. I know, not today. I tried. Oh, I was so excited to be like, wrong. Okay, and that's molarity of barium ions. Yes.
So you're only looking at
Correct.
if barium
Then it would not ask you for, or then the concentration would be 0. Yeah. But usually the question would ask you then for phosphate rather than barium. Great point. Okay, so let me just kind of go through the entire problem again, just to kind of give you guys a refresh. I'm not going to solve it again, don't worry. Just to talk through about how we got it, okay? First thing we did, we found the balanced equation, okay? We're good with that, right? And then we used our numbers to find the moles of each ion that we started with, okay? And then what we did was we figured out which ion we run out of. We figured out it was phosphate. And then we used this part right here to figure out how much barium is left inside the combined solution, and then we use the total volume to find molarity. So if you break it down into those steps, it's honestly not that bad. Yeah. Okay, just letting you know, you'll have a question like this on your test. So next time we meet, we will practice. So this is probably a problem you guys want to go over again, right? Okay, yeah, we'll go over this type of problem again next time.
For a second.
Oh, wait, I'm still recording. Oops, I was saying.
Mike is
Your final
we're all
answer.
off of you. Is it our break time?
Oh, I'm stupid. Never mind. I got the join code. Wait, never mind. I don't have it.
Air bubbles are like true.
Oh, with the gold? I mean,
Yes. Wait, right now? Is he gonna let us?
What's up? I'm still recording. Why am I? Acid,
Is there one for all?
nitrate, always lost. I think that's it.
Like the equation.
I'm gonna give you guys the equation sheet right now. Actually,
what does that say?
I think if I think of something, I'll let you know. Yeah.
And for the polynomial balance, just the same one.
Oh, thank you. Yeah, it's the same thing.
I
All right. So before we get into the next unit, the review for the gas stuff, we're gonna go over the equation sheet. So if you guys can take a look at your equation sheet. Again, you guys don't need to memorize any of this stuff. This is all provided for you on every one of our tests and on the AP test. Now, you guys don't need to look at most of it because we're not there yet. For your first exam, you only need this part right here. Obviously, the gases, liquids, and solutions part. And if you take a look, a lot of this is stuff that we already learned, right? So we got the combined gas law. We have the ideal gas law, right? We have mole fraction. We have the partial pressure. We have the equation for moles using molar mass. You have the kinetic energy equation. So you have the molarity equation, so on and so forth. Pretty much everything that you need. Okay, so I want you guys to just have this handy. It also has information like what STP is, right? The gas constant, so you don't need to memorize it. Okay. And so that is, and then they have all the variables. So that's all the stuff that you're going to have for the exam, so you don't need to memorize it. And again, I want you to have it as we do our review. Okay? Okay, so let's go over this together, and then we'll be all done. So gas stoichiometry. All right, so the first thing you want to do for this one is actually balance your equation. If you guys notice, it is not balanced, but I'm going to do it for you guys just for the sake of time. It'll be 2 here and 3 in front of the H2. Okay? So on your exam, if you had this, you would obviously be expected to balance, but I'm assuming that everyone is good at balancing, and so I just balanced it for you. Yes, that's how much I love you. Not at all. Okay, so we have some information. Let's go over it, and I'll show you guys how to set up this problem. So it's asking how many liters of a 0.1 molarity NH3 solution is needed to produce 5 million liters of nitrogen gas at STP. Okay, so a couple things we already know. STP, it's on your equation sheet, but if you remember, it is 1 atm, and the temperature is 273 Kelvin.
0.15.
Okay, whatever. All right, so it's asking you how many liters of this we need in order to make 5 million liters of this. And so we're trying to convert from N2 to NH3. Now, if you remember, whenever we're using a conversion using a chemical equation, we always need everything in terms of moles, right? And so what we are trying to find is we're trying to find moles of nitrogen so that we can turn it into moles of NH3. And so that's where we're going to use our information about the gases. Okay, we know that the pressure is 1 atm. We know that the temperature is 273. We got the volume right here, right? We got 5 million. I'll see it. 5 times 10 to the 6 liters. And so we need to find N. So what can we use in order to find moles? Yeah, ideal gas law. We're going to use PV equals nRT. So I'll pause right there. See if you can take about 2-3 minutes and convert into moles using this information right here and the ideal gas law. Okay, just a reminder, the constant R is on your equation sheet, so you don't need to memorize it. You can just copy it down exactly as is. And then if you feel comfortable solving the problem all the way, go ahead. But in about 2 minutes, I'll go over how to use the ideal gas law, and then we'll do the final conversion. All right, guys, so let's start wrapping it up. So ideal gas law, I rearranged it. You don't have to rearrange it if you don't like doing it, but you should get this big value for moles of N2. 223,081.83. Somewhere around there. Okay, now we need to convert this into NH3. So what we're going to do is we're going to take our number 223,081.83 moles of N2, and then you use the balance equation. It is 1 mole of N2 for every 2 moles of NH3. And then you can do it the way that we did. Solve for moles, convert to liters. I'm going to do it a little bit faster. We know that molarity is moles over liters. So we know that if it's 0.1 molarity is 0.1 moles for every 1 liter. And that'll give you liters directly. If that part didn't make sense, just do it the way that you normally did it.
And can you still do that on the other problem we did?
You could. You can do that for every single one of the conversions we did.
So why are you simplify?
Because math is hard. I don't want to confuse people.
That's so much less.
And this will be your final answer for liters of NH3.